Well, good morning, everyone, and welcome to Finland. The topic of my presentation is the next generation Ionoplast for improved processability, and I'm going to talk about some of the development of this product and some of the challenges that we faced. So the topics I'm going to discuss today are, just to give a little bit of a background for people that don't know what structural interlayers are. So what are they? What are the different types of structural interlayers on the marketplace? And then get into the meat of the development of the next generation Ionoplast. So what were the goals? What were our challenges? What were the lamination process improvements that we were able to achieve? And also, what physical properties, what were the comparison of the physical properties of this next generation Ionoplast compared to the current Ionoplast? So, what are structural interlayers? I'm sure you've been hearing more and more about them over the past years coming to GPD. They've been becoming more and more popular and used more prevalently, particularly since architects and engineers are continually trying to push the boundaries of how glass can be used in building, and they're developing extraordinary building designs that incorporate glass in such unique ways using minimally supported, less framing, less metal attachments. So they are high modulus stiff interlayers. They increase both the strength and safety of the glass beyond typical laminated glass, which allows glass to be used, as I was saying, in such extreme applications as minimally supported, large glass panels, floors, stairs, and bridges. They're able to handle higher loads with less deflection, and this gives you the option to lower the glass thickness. So in the end, they can actually save you money. And also, one of the biggest benefits is the improved post-breakage strength. So I talked about improving safety. So if you look at the evolution or glass in terms of its safety performance, the basic safety glass is tempered glass, and in some regions that's considered safety glass. And it does provide some strength, and it does provide some protection. However, once it's broken, and the pieces of glass can become dangerous and can cause injury. If you then take that one step further and you laminate it, you've now already greatly improved the safety, because you've improved so that when the glass breaks, the glass shards adhere to the inner layer and prevent injury from the glass shards. However, the post-breakage strength is not necessarily improved. In some cases it is, depending on the glass type used, but there's still a vulnerability and a weakness in the post-breakage glass strength. If you want to improve that even further, you go to a structural interlayer. Not only do you also have the post-breakage glass retention properties, but now you have post-breakage glass strength. So that's the evolution of improving glass safety, going from basic glass to structural. So what are the types of structural interlayers on the market today? There's two main types. There's the Ionoplast interlayers, and these have been around for 20 years. They were originally developed to address the very specific needs of the hurricane market after Hurricane Andrew, and have now since been known to be used in extreme structural applications, and has been known as the gold standard of structural interlayers. They're based on ionomer chemistry, so completely different chemistry, and it's this specific type of chemistry that also causes it to have some different needs with regard to how it's processed in the lamination process, and I'm going to talk about that in a little bit. They have superior optics and edge stability, and there's no plasticizer. It's because there's no plasticizer that you have such great edge stability. And the modulus maintains its high modulus over a broad range of temperature and load durations, which is why it's used in a lot of extreme applications. But because of its unique chemistry, some special processing is required, and I'll go into that in a little bit more. Stiff PVB interlayers are based on PVB chemistry. They just have a lower plasticizer content, and they have very high modulus. The lamination process is the same as PVB, so that's the advantage of it. There's no need to change your lamination process. So I mentioned that Ionoplast requires some special processing, and some of the things is that it requires you to laminate the glass to the tin side and to get adequate adhesion. If that is not possible, such as in multi-ply layers or in laminating to frits, you must use an adhesion promoter in order to get adequate glass adhesion. You also, because of its unique chemistry, Ionoplast interlayers are semi-crystalline. Unlike PVB, they have crystallinity which is affected by cooling rate. There's just nothing you can do about that. It's the crystallinity in the polymer that gives it its strength. It's also the crystallinity in the polymer that causes this issue with haze if it's not adequately cooled. Now, we recommend, a cooling rate of a minimum of 2.2 degrees C per minute. But if, the laminate comes out of the autoclave and it does have haze, you can always re-autoclave it. So this is a reversible thing. So it's not something that can't be changed or prevented. It's just something that you have to ensure that you take care of in your lamination process. So sometimes this causes difficulty in large laminates or in very thick laminates. Very thick laminates that are used in some of these structural applications, or very thick laminates that are used in bullet resistant or bomb blast. It can be difficult with that mass to be able to have adequate cooling rate all the way into the core. So now I want to move into and shift into the goals and challenges of developing the next generation Ionoplast. What we really wanted to do is eliminate some of these requirements that are in place for the current product. We wanted to improve the processability and make it more like PVB as much as we could. So we want to improve the adhesion to the air side of glass. We want to reduce the haze dependency on autoclave cooling rate. And we want to have the adhesion less sensitive to moisture of the interlayer. We also want to enable it to have a more robust lamination process so that the laminator is confident in the final quality of the laminate will be consistently of high quality. The challenge, though, so this is the challenge. You always have to defy these basic laws of chemistry, basic laws of physics. In doing this, we also want to maintain these really great properties that make Ionoplast unique. We want to maintain the high modulus over a wide range of temperatures. We want to have excellent post-breakage strength. And we also want to maintain the current impact properties that it must meet for the industry standards. I'm going to go into the processing improvement results. I'm going to talk about how we improve the haze formation versus autoclave cooling rate. I'm going to talk about the adhesion to the air side of the glass. And I'm going to also show some data on the adhesion robustness in the presence of moisture. This graph shows the effect of cooling rate on haze formation of the new Ionoplast interlayer versus the current Ionoplast interlayer. And you can see here, this is autoclave cooling rate. So these are cooling rates that are much slower than what we recommend, which is 2.2. So this is really pushing it to the very slow cooling rate. This is the current Ionoplast, and you can see the haze formation much more dependent. So just for a reference, if this was PVB, or a stiff PVB or a standard PVB, this line would be completely flat. There would be no dependency whatsoever. So you can see we're starting to get closer to that no dependency, but there still is some. Remember, it's a semi-crystalline polymer, so it's you're going to have some dependency. So what does this mean? This means that there's a potential here for laminator to increase their load density in the autoclave because they don't have to be as concerned about getting enough airflow around the laminate. So potential to increase throughput through the autoclave. Improvements to the adhesion to the air side of glass. This is a graph showing pummel adhesion, room temperature pummel adhesion. And this is next generation Ionoplast. The orange is the tin side. You can see we have good adhesion to the tin side as expected. But then if you look at the pummel adhesion to the air side, you see that it is greatly improved so that there's basically no difference between air side and tin side adhesion. Now that's with no adhesion promoter. If you use adhesion promoter with the current Sentry glass, you have good adhesion also. So this is showing it without adhesion promoter. And this is pummel adhesion, which is Again, at room temperature, and it's based on standards where you pummel the interlayer, you pummel the laminate, and then you look at how much glass retention is remaining and compare that to a standard, and it gives you a grading. So that's just in case people here don't know what pummel adhesion is. So another thing we wanted to look at is how robust is the adhesion with moisture. And so we recommend that people keep their Ionoplast at 0.15 moisture or lower. So we tell them to seal up the bag if they open it and keep it, in a semi-controlled environment. Just take care to prevent moisture from getting in. The good news is that Ionoplast doesn't pick up moisture fast. But the bad news is that when it does pick up moisture above 0.2, you tend to see a dropping of adhesion. So this graph shows the orange line is the tin side, and the dark line is, this is the air side, and this is the tin side. And this is interlayer that had been left exposed to ambient conditions up to 21 days. And you can see you go from a moisture of 0.1 to 0.35% in that time, and you still maintain adequate adhesion. So this just gives more confidence to the laminator that they're going to have good adhesion if, something were to happen and the bag was not exactly sealed. Okay, so I've just showed you that we can improve the haze dependency on autoclave cooling rate. We can improve the adhesion to the air side without the use of primer. The adhesion is more robust and less sensitive to the effects of moisture. So now I want to talk about the physical properties. Remember the challenge. The challenge was, can we make it process more like PVB while still maintaining these structural properties of the current Ionoplast? So I'm going to talk about modulus versus temperature, an overview of the physical properties, impact performance results, and then some post-breakage. So if you look at modulus versus temperature, and this data was collected by using 3 different methods. We used DMA, bending studies, and creep analysis. I'm not going to get into the whole discussion about methodology because that's something that's been a big debate lately, that we need to come to a common standard test method for developing these types of data. But for now, this is what we have done, and you can see that I have stiff PVB here as kind of a benchmark, and this is our current Ionoplast and the next generation. So you can see it is lower. You do have lower modules in the current, but we believe it's sufficient enough for coupling, and it's much better than stiff PVB. So I'm just going to go through 2 load scenarios just to show you. This is a minimally framed glazing system using 35 degrees C and a 2.2 kilopascal design wind pressure. And I want to just show that in the current Ionoplast, you have the maximum deflection and maximum principal stress. And in the next generation, you have the values for that, along with the Young's modulus. And you can see that it is a little bit. You have about a 0.04% increase in principal stress, 0.36% increase in deflection for the 3-second, and here's the values for the 5-minute and 10-minute. So it does have a little bit more deflection and a little bit more stress, but if you compare it to the stiff PVB, it's still much better. So the next one is higher temperature. Remember, one of the goals was to maintain the structural properties over a broad range of temperature and loads. So this is at elevated temperature, which was our bigger concern. And so here we have current Ionoplast, next generation. And here you have, at a 3-second duration, 0.5% increase in stress, 5-minute duration, 3.3%. So a little bit more, as expected. But then you take a look at your stiff PVB at the 3-second load duration comparison with the modulus that it has, and you have a significantly higher. So it does have a little bit more deflection and a little bit more stress, but still very high modulus and very good structural performance. Impact performance. So one of the concerns we had is maintaining its impact properties, and when you increase adhesion, you can negatively affect these. And so we wanted to see if we could pass the same constructions we do with the current Ionoplast, and we do. You can see for 0.89, we passed the ANSI Z97, EN 1200, and EN 356. The only thing that was an issue is the hurricane impact testing. We did have to go up a little bit in caliper to pass the large missile impact. So again, as I said, in the impact comparison, improving adhesion can negatively affect the impact performance. The next generation Ionoplast has the same impact performance in most cases, except for in the large missile impact for hurricane. And now I'm going to move on to post-breakage testing. So we've conducted some room temperature post-breakage testing. We have elevated temperature post-breakage testing underway, and we wanted to see and ensure that they were going to be comparable. So we did the same testing that we've done with our Ionoplast in the past, where we used 6 millimeter tempered glass and a shot bag dropped at 1.5 meters. And this is at room temperature, and you can see that they have pretty similar performance. They both, after breaking, still stand up. Okay, so in conclusion, I think we have really achieved our goals quite well and met the challenges, and have been able to develop a next generation Ionoplast with improved lamination compared to the current Ionoplast. We've improved the adhesion to the air side, eliminating the need to use primer, giving better confidence in the final quality of the laminate, and also making things easier for the laminator, not having to worry about having primer and applying primer. The haze is definitely much less sensitive to autoclave cooling rate, not completely eliminated, but much, much improved. The structural performance is still very close, and still provides that structural performance over a broad range of temperatures and loads, like we were trying to achieve. Post-breakage performance at room temperature is equivalent, and the impact performance of the next generation Ionoplast is the same as the current Ionoplast in most cases. And I thank you for your attention, and I have like a minute left.
All right, thank you, Jennifer. Is there any questions?
Unfortunately, we don't have a vacuum autoclave, but a vacuum.
Okay.
So does the same principle apply? By cooling and...
Yeah, I mean, the same principle applies as far as giving yourself good adhesion to the air side. If you're doing multiple plies, I think you'll still see some benefit of the lower haze in that process. We haven't done a lot of work in non-autoclave with this product, but you should see some improvement in that.
Any?
Hi, Jennifer.
Hi.
Now that the new extra product, it shows a better or less haze on the laminates, especially when you do multi-laminates and thicker laminates. So the color will change. Have you done any testing on the wavelength color and a new LAB data?
So we have, and it's pretty, there's not much difference in the color. What you do see is if maybe you're talking about the edges in low iron, you're talking about straight through color. So we do have we have done LAB. As I recall, it was very similar to there wasn't a whole lot of difference in the polymer color. In fact, taking that back, there's less color. So what happens is when you have the haze in there, it tends to give you a blue color type effect, and there's less of that. But I don't have the numbers.
Well, do you have the numbers?
I can send you the numbers. We've done it, I just don't remember them. I will give them to you.
Any further questions?
And what is the time frame for this new Ionoplast interlayer to become available commercially, and would it also be available as rolls?
Yeah, so we launched it in sheet commercially in February. Our plan is to have rolls available by the end of this year.
And it will then replace the existing one?
So no, we don't plan to replace the existing one. We plan to offer it to complement the current product for those laminators that have value for the improved processability.
So it has a different branding? Or is this something that we would request, or is this something that would be at the discretion of the supplier?
So you can request it. We do have drop-in spec name for it. It's called Sentry Glass Extra, and you can specify it that way. I believe Valerie Block has a couple different ways you can specify it to ensure that you get it.
And what about the effect of the anisotropy on the interlayer?
So we have done some work with infringents, and we have found that it improves it. Anisotropy is complicated because there's effects of glass, there's effects of things, but with regard to birefringence, that sometimes happens with current Ionoplast because it's so stiff and non-compliant, it can cause stresses, and you see those lines. Because this is a little bit more compliant, you don't see that as much. So yes, we've done it and we see improvement.
Okay, looks like we're out of time. Thank you, Jennifer.
Hi there. Did you like what you just saw? If you did, why don't you like the video, drop us a comment below, and share the video as well, since GPD is all about sharing. And to receive more videos in future, subscribe to this channel and don't forget to click the bell icon. Ciao!